Yeah, hi. So I guess we super slowly get started. There's still people joining on Zoom. I hope everybody can hear me loud and clear. I mean, we did already a check. Just for information for the people on Zoom, we disabled the global chat because we had some problems with Zoom bombings in the past, but please feel free to just write me a message. I'm following the chat as we're going along, and I will be able to read it. And if anyone has a question via the chat, we can also unmute you if you are online. And of course, here the people in the room, since we are live streaming this, please make sure you use the microphone when you ask a question. Then the camera will zoom on to you, and people who are following you online can also hear your question. All right. So let me just briefly start. So my name is Michael Herbst. I'm a new tenure track assistant professor here at EPFL. I started like a few months ago. And one of the things that I'm doing is I'm working a lot with Julia, the Julia programming language. And basically, one of the things that we came up in discussions with other people is that I would really briefly give an introduction, say a few words about the Julia programming language and why, in my opinion, it works so well for interdisciplinary research and basically materials research. So just for your information, if you just Google Julia for materials modeling in GitHub, you will basically first hit find the material for this repository. It's done in so-called Pluto notebooks, which is essentially like a Julia-based alternative to Jupyter that I will also briefly speak about in the talk. If you can't be bothered to install Julia just to look at this stuff, there's also statically rendered material out there. You can basically just click on these pages and you get a statically rendered version of what I'm going to present to you today. Okay. So let's get that started. Basically what I'm going to talk about today is first a little bit about Julia itself. This is just going to be something like maybe 10 minutes. Basically show you like the key features, what's going on, and why I think it's an interesting language. Then I will talk a little bit about one showcase, well, the so-called density function toolkit. That's exactly the tool I'm working on in my group, and basically show you as a showcase what you can do with the language and why, in my opinion, it works so well. Then I will go into more, let's say, the ecosystem. I will talk about some of the packages, some of the efforts that people have been doing in the past. I'll talk about something which has just been very recently, Veneerization. I think it's an interesting topic where we have two Julia tools working together. I talk about some tools for machine learning. The ACE model you might have heard is one of the things where people are specifically working in Julia. And then here in the end, I don't think we will get there, but this is essentially an overview of some more potential packages that could be interesting for you to take a look at. Okay, so let's get that started. So basically, Julia was started about 10 years ago. So now it's pretty much 11 years old, really. And yeah, why did it get started? Well, essentially, it's really the frustration over tools that have been out there that really got four people together, basically centered around MIT, and they really started to work on this Julia programming language. So essentially, the point is, all the languages that are out there, they are good for some things, but they have issues. So why not make a language that can do everything, right? So this sounds like a big promise, but in fact, in my opinion, they really got as close to it as I've ever seen before. So I myself also have a background in C++. I did Python, Fortran, all the standard things. And now I do Julia, and I really hate all the other things in comparison, right? So you see, I mean, I'm definitely also one of the people that has exposed, and I got frustrated, and now I'm actually considerably happy. I mean, not that Julia has no problems, it has a few, but I'm definitely more happy than I was before. Now, maybe before we go into the details, what is really a good scientific programming language about? Well, in my opinion, it should definitely be fast and scalable. Nowadays, HPC is, it's out there, right? We should, whenever we write a program, it should work on HPC. Interactivity, science never works by just running a program, getting the answer, and I'm done. It's always about, interactively gaining insight, analyzing results, starting new calculations, and so on and so forth. So this iterative process, this interactivity is really crucial. Easy to write and read. We all know the problem. PhD student is around for 3 years, 4 years, then he disappears. Next PhD student comes, has to read the code and start working on top of it, right? So if the code is not easy to write and read, that's basically just killing half a year to a year of the potential time of every student. So that's a crucial thing, especially for university research. And based on basically number 2 and number 3, I'd say key thing is also that users and developers of scientific codes are the same people, right? So this is really something we need to understand. The people who write code and the people who use code, they should sort of meld together, right? Because the people who use the code know the problems, and the people who develop the code, they provide the solutions. And ideally, those are the same people, in my opinion. So, I mean, I think I don't have to go into more details than just saying all languages that are out there. I mean, you know them probably. There's essentially trade-offs. So what people typically do is they mix stuff, right? So they mix, for example, Fortran and Python, C and Python, typical things. But that leads to the so-called two-language problem, because you have to cut somewhere. Somewhere you have to make the decision, this is what I put in Python, this is what I put in C. Okay, and then whenever really you sort of transfer features, you either rewrite them, which is sort of a deal breaker for what I call iterative performance improvement, right? So it's, if you improve your performance, at some point your Python code is too slow and you have to write it from scratch, right? And that's, you know, that's a huge amount of effort, and then usually it doesn't bring you too much gain, right? So that's, at some point, the effort you put in versus the payoff you get is sort of non-discontinuous, and I think that's a problem. You might disagree, but we can discuss about this. I'm very happy to go into more details. Then I think really, yeah, when do you do this, right? So along the lines of this being so much effort, when do you actually make that this decision is not so easy? And also, I think it's really an extra barrier. You know, learning one language is hard. Now try 2, 3, or 4, right? I mean, it's really this, you have to know more than one language. That, in my opinion, is a bit of an issue. And of course, something that one of the founders of Julia always says, and I think it's an amazing quote, Alan Edelman, he says, people compose if software composes. And I think that's very much true. In science, and I mean, especially in interdisciplinary science, I've often had the problem that collaboration stopped before they even began, because people said, okay, I mean, we have this code, this does that, we have that code, this has this feature, now let's throw them together. And then, well, actually, that would take a PhD student to rewrite half the code, right? So these things happen, and that's a problem. So codes should compose, because then we can do the science. Okay, I think that's pretty much all I want to say in a presentation form. Now we get a bit more hands-on. So I want to show you some code. I want to show you basically all of the things I'm going to show you today is by examples. So basically the things should hopefully work. Demonstration-based presentations are always a bit of a bitter thing. So let's hope for the best. But yeah, anyway. So what makes Julia nice? Just 2 key things on that one, or 3 key things. First, unlike Python, for example, it has arrays. So basically the key linear algebra stuff is immediately out there. You can easily make arrays. You see, we can also use scientific symbols, which in my opinion makes code a lot more readable. We can do simple additions. We can do vectorized operations, right? So Julia has the built-in notion of a vectorized operation, which is extremely great if you think about the fact that nowadays vector processing is really everywhere. This just doesn't just work for built-in stuff. We can just make our custom function and chain it with things. And this is really an enforced vectorization. So at this point, the Julia compiler has to vectorize, right? So it's in my opinion, one of the things which is really strong. Another thing is, compared to, for example, Python, loops are no longer slow, right? So here I just write up an addition function for basically vectors or matrices or something like this. I go over basically all indices, I add it all up, and that's it. So that's really how you would want to write it, let's say, okay? And in reality, if you compare it to the standard matrix addition here, that is sort of provided by BLAS, you see, I mean, sure, it's a bit slower, but I mean, these are really like MKL style low-level optimization that make this difference. So even with plain simple Julia code, you can get almost there, right? And this is true. I'll show a more elaborate example in a second. This is true for many things. Standard linear algebra is implemented. So this does a transposition, for example. We can then just call an eigen function to do an eigen decomposition. Okay, so far, I guess you're not amazed yet. But now comes the amazing part, because in fact, we can tell the compiler if we know properties about our matrix, right? So here we can tell it explicitly it's symmetric. And in fact, it will sort of automatically use this type information, propagate it through, and it will call a slightly more specific version of the diagonalization. We can do this with even more special things, even with our own types. And in fact, here you see that there's 38 specific implementation of the eigenfunctions in the standard library, which really, like, based on sort of the type, based on the properties you annotate the matrix, will pick the right thing. And the key thing is that the place where this picking the right method happens and the place where you really define the matrix, that might be completely two different codes, right? So you as the user who knows the physical model can annotate the physical properties, and somebody who writes an algorithm doesn't necessarily need to know all this, but can still benefit just by basically implicitly using the right method. So that's quite strong. And yeah, in my opinion, one of the important features of the language. Next thing is for teaching. Julia and the Julia ecosystem provides you a lot of cool stuff. So you see it's really easy to build in interactive elements here. So here I'm selecting a slider, I'll select a frequency, and here I'm just plotting it. So you see it's all very nice. This works also for debugging. So here I can really, like, for example, interactively, I have a test here, and you see I can, step by step evaluate the expression and understand why things are true or false, right? So these sort of things, these interactive elements are really are not necessarily built into the language, but they are provided by the ecosystem. It's really easy to use them, for example, in a presentation like this. Package management, in my opinion, is a big deal in science. So here you see what it looks like in Python. Julia has the advantage of being a bit more modern. It's definitely done a big improvement. The package manager is built into the language. It creates automatically reproducible environments. So like Conda, for example, if some of you know this is sort of standard in Julia. It handles dependencies and versioning. This includes third-party dependencies. So here I'm using Julia's package manager to install Quantum Espresso and run a Quantum Espresso calculation, right? And so these sort of things happen, right? I can write a Julia package where I specify I want to use this version of Quantum Espresso, and then I have it. And whenever you install my package, Quantum Espresso is installed as well. Right, and you see it really works. So here's the calculation, does a few iterations, and I mean the details don't matter, and then gives some output, right? So just to prove you I'm not cheating. Yeah, along the lines, combining with existing code is easy. C in Julia, Python in Julia, no problem. Both ways, in fact, in both these cases, there's also things for R and Java and so on, right? So we have a strong package management, we have strong combination of packages. And now I want to do one more short Julia-specific detour on the speed. And the example I'm going to pick here is, in fact, summing all elements of a vector. So again, I have a very simple Julia implementation. I take a vector, I have a zero accumulator, I go over all the elements and sum it up. And I'm doing this with a particularly large array of numbers. And I'm doing this in a couple of, let's say, languages implementations, and I'm storing the results in a dictionary. So that's the sort of setup. I don't have the time to go all through the details, but if you want, the details are all there in the notebook. The key point is in Julia, like this is in C. I'm writing a bit of C code. I'm actually compiling and calling it from Julia just to make things simple. But I mean, this is essentially a C implementation of exactly what I just presented to you on the Julia side. I also have an explicitly vectorized C implementation, which, as you see, is ugly and twice as long. And I do basically a benchmarking, a certain number of samples. And you see the C implementation, the vectorized one, is in something like 4 milliseconds. Here we have also around 4 milliseconds for the non-vectorized one. The Julia version that I just showed you has 11 milliseconds. So you say, got you, right? Slower. But actually, I haven't used all the tricks. Namely, Julia does explicit bounce checks. So of course, in this case, when I'm actually explicitly looping over the length of the vector, the bounce checks is a bit excessive. So I'm disabling this. And I'm also giving the compiler here with the appsynth macro a bit more freedom to apply vectorization. Again, I'm very happy to discuss the details, but essentially in this case, it's completely fine to do it. And you see I'm more or less down to the same speed. I can also do this in Python. So NumPy is basically as fast as here we are, as fast as the Julia version is, because in fact it's using a hand optimized C implementation. I can also do it in plain Python, and there it's just horrible. Okay, for 16 seconds. So here's the overview, right? So the key point to get across is plain and simple Julia is obviously like a lot better than for example, Python. But with simple and completely reasonable tricks, we can get it down to exactly the same speed as a C implementation also gets you. Okay. I don't want to spend too much time on this, but it's not just fast, it's also extremely flexible. So for example, I can use this function with not just with standard numbers, I can use it with very high precision numbers for cases where basically summing things up can get messy. I can use techniques, so-called interval arithmetic, to track numerical error automatically. Or I can do things, which this is an example I really like. So for example, if I want to solve a differential equation here, right, I usually have some parameters, but usually I don't know the parameters so exactly. So if I just solve the equation, I can, for example, produce a plot of the result. But now the only thing I do is I change the input values from being plain numbers, but to be numbers annotated with some measurement error. And you see, I can basically, that's all I do with this bar. And you see automatically everything updates. And this really works because all of the packages are written in this high-level Julia style. Okay. And therefore, fundamental changes like the change of the floating point type can really propagate deep into the packages. And what is absolutely crucial in this example is the people who developed the plotting package, the people who developed the differential equation solver, and the people who developed this measurements package, they didn't talk. Okay. So somebody just had the idea, let's try these three packages together. And it just worked. And this is something that happens quite a bit in the ecosystem from time to time. Okay, now I have to be honest, they did talk, but they found out that it's actually like 2 or 3 lines of code they had to change, right? So the point is, yes, it takes a bit of effort, but the effort is like compared to other languages, it's really small. Okay, I'm just gonna pause here for a second, giving people the chance to ask maybe 1 or 2 quick questions. So people who are joining us online, please write to the chat if you have a question, and then you will be given permission to open up your mic. Does somebody here have a question at this stage? 1 more second for the chat. Yeah, so somebody has a question. Can you do the honors, Junfeng, and just give the person the permission to speak? Or you don't see any questions. I think there is one. I'm not finding the person. How can I unmute? Okay, so we see the video. How can I unmute? Patrick?
Maybe call the name of the person because you might not know it's there.
So yeah, Liam Marsh. I basically. Okay, so he put the question into the chat. That's a good idea. The SIMD decorator, is it actually doing SIMD stuff, or there's also multi-threading over the loop? No, this is not multi-threading. This is just doing basically allowing the compiler to do a few more optimizations down the line. It's not multi-threaded. There's packages to do that though, that also do multi-threading and chunking and all sorts of things. Loop vectorization is such a package. All right. Yes.
Just a quick one on the package management. Is there any way to install Julia in a Conda environment? Because it's not really a solution to give Julia the topmost packaging responsibility, because there are many things outside of Julia that you want. That you can already get.
I think Julia is packaged inside the Conda environment, but to what extent you can then use Julia packages, I honestly don't know. But yeah, I would imagine that there's maybe some ways to do that. Yeah. All right. Let's quickly move on. So the next thing I want to give you basically a brief showcase over is the density functional toolkit. So the density functional toolkit is basically a DFT code that we started from scratch about 4 years ago. We really integrate into this Julia ecosystem, so like arbitrary precision and things like GPUs, MPI, and I mean also a few of the things that I just showed you, interval arithmetic and so on. These things are all basically working with our code. Yeah, we have something like 7,500 lines, and it's pretty much a DFT code going. Yeah, has a bunch of features. So, for example, here's a feature overview. If you wanna take a look, it has basically recently most UPF norm-conserving pseudopotentials and GGA meta GGA functionals. So it's you can do things with it. It's the key thing. Yeah, for example, just to give you a small hint at how it works, you basically, for example, here I have a quantum espresso calculation of that I just showed you before, so antiferromagnetic ion, and I would argue an input file like this is perhaps not the easiest to read, right? On the other hand, on the Julia side, here we can, for example, use a package system known as atom space, which is integrated with the atomistic simulation environment. And basically with this, we can just build the system, right? So using, if you know it, the atomistic simulation environment, I very easily build my system of ion. And then I can, for example, really convert it to the Julia side. And you see I get a very nice output. And this I can directly use in a DFTK calculation, right? So here I can either here I can basically just attach a pseudopotential to it. Like I tell it, okay, use the system, use these pseudopotentials. And then I basically make a model. Here, make a PBE model. I use some smearing, select certain discretization parameters. And yeah, I basically get a nice output, which sort of summarizes the setup. So basically in 4 lines of code, I have done all the setup. I can start my density. I can basically create some guesses and then run the self-consistent field calculation. And in my notebook, I then have all the information available and can, for example, here just print the total energy. Okay, so this is more or less a standard DFT calculation done in, I don't know, maybe like 8-10 lines of Julia code. And you see, I was quite flexible. I can now, for example, I could generate any file. I can also I could generate any system. I could also, for example, read an input file. I will show you in just 1 second how this works. And basically with a few lines of code start the calculation. Now this is sort of standard. Next thing I want to show you is how to do calculations on a GPU. So this laptop has a GPU, so I can do a calculation on the GPU, and that's it. That's how I do the calculation on the GPU. So again, I build a small system, silicon, I attach a pseudopotential, make a model, and then run the calculation on the GPU, and this is all I have to do. Right? This is the change that tells DFTK, by the way, please use a CUDA array to represent all your data. And this was 500 lines of code change. So from the 7,500 lines we had to change 500 lines of code. This was a bachelor student in physics, 10 weeks of work, and we have GPU support. And I know exactly what needs to be done to extend this to AMD GPU and other GPUs. So if somebody wants to do a student project, I think that's a realistic amount of work for a student project. Please get in touch. Anyway, so yeah, that's one of the cool things we can do. GPUs is there. Next is algorithmic differentiation. Okay, so let's say I want to understand, I'm doing elastic stain engineering, I'm doing materials design. I want to understand how does the band gap change if I change the lattice parameter, okay? Right, so how does my band gap change when I change the lattice parameter? So I want to understand the derivative, the band gap over the lattice parameter. Okay, so let's compute it. Here's a function that computes the silicon band gap. It sets up the lattice, does again the discretization, everything, does the SCF run, and then it basically just finds the direct band gap, right? It goes through all the eigenvalues, finds the convection band minimum, valence band maximum, and has the band gap, okay? Now, the only thing I have to do is I use this function and I call I use a package for algorithmic differentiation. And I say, don't just compute me the value, compute me the derivative. And that's it, right? I run this, it takes about a minute, and then I have the derivative of the band gap of silicon at the PDE level or LDA level, whatever, right? So these things you can just do. You can just ask for arbitrary derivatives. And again, I mean, the key point here is that's something everybody could do, right? You don't have to be a DFT expert to implement a new derivative. You can just ask the code a question in some sense, and it will give you the answer, okay? And I mean, using this algorithmic differentiation stuff, we also managed to do a stress implementation in 20 lines, okay? So whereas quantum espresso, just to give you an idea, takes 1,700 lines of code to implement stresses, we need 20. And if you don't believe me, here's the implementation. You can have a look. So it's literally taking the physical definition of the stress to do the computation. And the reason why this works is because stress is post-processing. So yes, we are slower than quantum espresso in computing the stress. But compared to the SCF, it's still a negligible amount of time, right? So in the end, we are slower, but we save a huge amount of code, making the code much more manageable and easier to work with. Next thing, just to give you an idea, we work a lot with people who do algorithmic development, mathematicians, right? And so let's say we want to implement our own SCF algorithm. So here I'm just doing a very simple row in, row out, plain mixing SCF algorithm. Again, I can use the dynamicism of the notebook, right? I could, for example, just see how it changes when I'm changing the mixing factor and so on. Right, so this is a very nice dynamic SCF solver people can play with in a teaching context, for example. And I'm just sliding it in here into the SCF function, right? That's the only thing I'm doing. And now I have a nice solver, and you see now it took 8 steps. If I'm reducing the damping, make the damping slower, it should take a few more steps. So it's doing a recomputation, and now you see it takes definitely a few more. Right, so you get the idea. I'm going back to point 8, because the next thing I want to show you is this actually works on the GPU. Right, so this is code I wrote, I can show in a teaching context, and yeah, you see, now it runs. This was my GPU doing the computation, right? So GPU coding of SCF solvers in a teaching context, no problem. Okay, and I mean, this custom code would also work with MPI and stuff. I mean, I'm not showing all this, but I mean, you could, right? And the key point is this works because this Julia code is actually compiled to a GPU kernel and running on the GPU. So if you've never done any GPU coding, by running my notebook, you will do GPU coding, okay? Yeah, I think just to conclude on this notebook, I guess I showed you really that the Julia ecosystem allows you to save code, still get performance, play easily with algorithms, and you can really orchestrate calculations on a high level, right? So it's really like you write a script. It's not writing an input file. And yeah, for really like in the past, people from math, from computer science and method development have already worked with our code. And yeah, I mean, I encourage you all to take a look. I mean, 7,500 lines you can read, I would say on a weekend, but I mean, I wrote the code. So maybe let's say in a week. So yeah, then you're up to speed. So again, I'm very happy to take any questions at this point. For people online, unfortunately, the opening the mic doesn't seem to work. So please type your questions into the chat if you have them. And yeah, people who are who are here are of course very happy to take the questions. Please, yeah, please use the mic.
So yeah, like for the algorithmic differentiation, is that again like the same instance you mentioned before? Like basically we implement a new floating point type that has
absolutely.
Okay,
it's exactly how it works.
So it's like 2 different package maintainers that didn't talk.
Yes.
Okay.
So if I mean, I do regularly Julia courses. I plan to do one here at EPFL at some point. Doing algorithmic differentiation in Julia is something which takes about 10 lines of code. It's really not that hard.
Okay.
Yeah.
Thank you.
Is there a question? Yes.
Can you hear me?
Yeah.
Ah, fantastic. Yeah, so
Great,
I was wondering. Yes, I was wondering about the auto differentiation with respect to like plus operations, because those I guess you can't auto diff unless you make a wrapper function.
With respect to what operations? I didn't catch the word.
To like plus operations, right? Like yeah.
Yes. Well, first of all, you could autodiff them if everything was implemented in Julia. In fact, some people are doing that, re-implementing Glass in Julia. But of course, at the current stage, you can't. But then you can write custom rules. I mean, in fact, for example, in this case, I'm not differentiating through the SCF algorithm because that would be far too slow. Instead, I'm actually doing a response calculation. So you can do what is known as custom rules. So you're sort of telling the AD system how a derivative for a particular primitive is computed. Yeah,
I see. Okay, fantastic. Thank you so much.
Any further questions? Junfeng, are we clear? Great. So let's move on. Next thing I want to show you is a bit the ecosystem. So I already mentioned the atom space system that I was using to basically generate a structure. Now, what I want to say is that in the past, let's say 2 or 3 years, people have really come together inside Julia from a bunch of different packages inside an organization known as Julia MolSim. About 20 researchers, I would say, respectively, maybe a few more these days, all over the world, Canada, US, Europe, Switzerland. And basically, yeah, the idea with this was to come together and sort of solve standard problems once and for all. And one of the standard problems is how to represent atomistic structures and how to make it possible for different packages to sort of seamlessly come together and talk to each other. And one of the things, as I said, atomistic structures is a key effort we have there. For example, I already showed with this with a package known as ASE convert, we can actually just use all the functionality from the atomistic simulation environment, come up with a structure there, and just directly convert it to Julia. So here's a case where I'm building a supercell or of silicon, and I'm just converting it to atom space. And because atom space knows how to display systems nicely in such a notebook, you immediately get this very nice visualizer, right? So the key point here is this is already 2 packages talking to each other without me having to do the effort. It's basically one package which takes data from the atomistic simulation environment, exposes it in this format of atom space that all the Julia packages understand, and a second package that just takes this information and makes a nice way of displaying it on such a web-based notebook, right? So this means any package that works with atom space has immediately this nice feature of displaying, right? So if you have your own package where you expose atomistic structures and you integrate with our interface, you get this for free, okay? Yeah, so the other thing is, of course, reading atomistic structures. So there is a package known as atoms.io, which uses actually in the back a bunch of other packages, including like chem files, external XYZ, and also the atomistic simulation environment, again, to really read a bunch of packages. So for example, I can read an external XYZ file. I could actually read a quantum espresso input and extract a structure and things like that, right? And again, it's very simple. I just load it and then I have the information and I can do stuff with it, like, for example, display it nicely and so on. And of course, I can do calculations. So for example, with this file that I loaded from scratch, once again, I can do a calculation. And in fact, because external XYZ files can store pseudopotential information here, I don't have to do anything. I'm just setting up the model. And yeah, I'm basically doing the calculation, get the total energy, right? And there's really a lot of packages now, like in the order of 10, I should be fair, that implement this atom space interface. And really, yeah, it's still rapidly evolving. So not all of them interoperate as nicely as I'm showing you this here, I have to be honest with you, but quite a few of them do, right? So this is something where you know, you can easily benefit from reading files and displaying them, for example. Another thing I want to show is Molly. So Molly is a package for molecular dynamics. So here, basically, in this example, I'm setting up a system with a bunch of Lennard-Jones atoms, very simple cubic boundary conditions, random initial velocity, Lennard-Jones interactions. I'm running the simulation for a few picoseconds, and then I'm storing the result here. I'm storing the result in this nice video, and I can, for example, take a look, right? So this is not super exciting, I guess, but I mean, in the end, still, it's a pure Julia molecular dynamics simulator. It's also currently being ported onto the GPU, actually in differentiable way, meaning that you can even differentiate, like use algorithmic differentiation through the GPU version of this package. So some people are currently working on this. Yeah, so that's atomistic simulation. Let's go for one more thing, Veneerization, before I do another round of questions. Yeah, so Veneerization, I think, is also a key important operation. And of course, we have somebody here in the room, Jen Feng, who has spent quite a bit of time to write a nice Julia-based package for Veneerization. And one of the things that happened is that us two really got together this time, and together with the other developers of DFTK, we came up with a way to, interface these codes in a very simple manner. And I just wanted to show you the sort of work in progress fruits of this, because I think it's a nice way to show again how two different Julia packages can work together, and nowadays are really able to do tasks that in practice can be interesting to take a look at. So basically, again, I have a nice setup where I basically do a graphene, this time a graphene calculation. I'm using a pseudo-dojo pseudo-potential, PBE model, some tunable ECAT values. So I'm just using 10 here to get everything run fast, but we can update it to, let's go to 23. And basically, I'm basically doing the calculations here in just a standard SDF calculation. Here I have some nice band structure that I compute with DFTK just to give us an idea how things are looking like. So now it's currently updating, you see, since I changed the ECAT. So this is still the old values, but I'm not going to wait for that. Then basically using the result from the DFT, I can start a Veneerization procedure. So basically I can very easily start with some initial guess. So this is the famous F function, the occupation function that is used for initial guesses in Veneerization. I can compute the resulting initial guess A, pass all of this over to some run Vanier that effectively really takes all the information from the DFTK guess, and starts the Veneerization procedure. And this is updating as we speak. So here we are. It starts the Veneerization procedure. In the Vanier routine, it takes here 72 steps to do the maximal localization. We have a Vanier output that we can, for example, use for band interpolations. And here basically we do again band interpolations and compare it with the original. And you see very nicely, this is the difference of the DFTK bands in gray overlaid with the Veneerization based bands in red. And as you see, they agree rather nicely. Okay, so key point to show here is we have a nice package. We have a nice notebook based setup where we can tune parameters as we wish. We can do our DFT calculation, hand it over to the Veneerization, get a Veneerized setup, and display, for example, the bands or do other things. And you can see, I mean, all of this is very nicely and interactive. I can really get going with this and interactively do my research. All right, I think this is a good place to stop once again and see if there are some questions about atom space, Molly, or the Veneerization stuff that I just showed. Yes.
So you said in Molly they were working to port it to GPUs. So how much work is there to take code that exists and make it GPU compatible, including autodiff? Because presumably all it's doing is manipulating primitives, arrays, things like this, which is already implemented. No, so what else do you need to do?
Yeah, so the difficulty, so first of all, GPU porting for MD simulations is tricky because if you just do it naively, it's going to be slow. Like things like neighbor lists are quite crucial. And that's not a standard primitive, like in the sense of computer science, right? It is in the sense of molecular dynamics, but these sort of very important primitives that, in the end are the step that cost your quadratic or whatever time, right? So this is the time consuming step. So you need to get custom kernels working for that, custom GPU kernels, and that takes effort. I mean, in whatever language, right? You have to write it. And this also answers the question regarding the differentiation, because now if you want to do a differentiable molecular dynamics simulation, you have to differentiate through these custom CUDA kernels. And that is nowadays possible, but it's still very tricky. So this is exactly the part what people are working on right now, to make it not just work, but to make it work in a reasonable and, well, competitive, I'm not sure, because it's actually, I mean, MD codes are quite well optimized. So to at least get close to the competitiveness of other codes, let's say, yeah. All right, I guess we move on to the last bigger chapter I want to show for today. And then if there are more questions, I'm of course very happy to answer them. So the next thing I want to talk about is the Julep and ACE ecosystem. So this is basically machine learning based on the atomic cluster expansion, for which there's really a huge amount of packages out there. Well, not a huge amount of packages, but it's basically a well-developed ecosystem of Julia packages that allows you to do these type of molecular dynamics, these type of machine learning and interatomic potentials and treat with them. Yeah, so basically the way it works is that, again, Julep is, if you want, a little bit an alternative to the atomistic simulation environment. So it's sort of a pure Julia-based implementation that people have developed around, people like Christoph Ortner and James Commode and so on. It's like the main driving forces behind it. I might forget a few, so I apologize. But the point is that this is really something where you can, very easily assemble similar to the atomistic simulation environment, like supercells, for example. And very recently, what is quite nice, and I'm personally quite happy about, is that these Julep structures that you see here can now be easily converted also to atom space. So all of the benefits, like the visualization you see here, are now also available to this Julep ecosystem. And you see in the end, it's really simple. Here you have the Julep structure, you convert it to an abstract system, and in the back, it does all the unit conversion and all the funny and annoying things for you. And of course, we could now also use this to do calculations, but I mean, I'm not going to bother to show you this. Instead, what I will show you is that Julep is actually quite nice to build custom analytic, for example, or custom interatomic potentials and play with them. So here I'm just building a very simple analytic potential. I basically just code the expression here. I have a few parameters, and this very little code here defines an interaction between atoms, and I can directly use this here in combination with these atoms that I just made up here to basically compute the energy, right? So you see in a few lines of code, I come up with some custom potential, and I can do an interatomic potential evaluation. And this has an interface which is basically very, I hope, in my opinion, quite nice and quite useful. And standard potentials are of course already implemented, but if you want to do some research on this, you can very easily play with it. In fact, actually, one of, if you want, these custom potentials that can be put on top of Julep is the this ACE family of models, the atomic cluster expansion. It's really like here it's an organization, the ACE Suite GitHub organization, that features a bunch of packages for building these ACE machine learning models, for fitting them, as I said, for using them, and also for validating and so on. And just I'm basically copying this from one of the tutorials in this ACE1 package to fit this type of titanium aluminium potential. So it's using here some pre-computed DFT data that I'm loading. And for example, here I'm just fitting the data. I'm basically analyzing the data. I'm setting up an ACE model with a certain order, a certain polynomial degree, if you know the details. If not, it doesn't matter so much. I'm basically setting up such a model. I can find some weights, and then I can theoretically fit. I have to admit I didn't get this to work, so I'm not really able to show you. But in principle, according to the tutorial, this works, right? So I can basically fit the model, and then based on this, do some error analysis, and really in the end do an evaluation of my thing, which here is garbage because I didn't train. But I mean, in principle, this is how it would work, right? So just to give you a very clear, a very simple idea. So this really allows you to play with ACE models, set them up, and yeah, directly use them in combination with these julep type structures, which, as I just said, is really, again, yeah, according to some recent effort, is really in place compatible with atom space structures. All right, I think this is another good time to make a small cut and then see if there's a few more questions. All right. So there's maybe one final notebook I can very briefly show you, just to sort of mention what else is out there. So I already talked about Atom Space, which is really, in my opinion, one of these core packages to get other Julia packages to talk to each other. So yeah, DFTK supports it, Molly supports it, Julep supports it, and there's a bunch of chem files and ASE-based parsers in this Atoms.io, for example. There's another effort that goes on inside the MIT. It's a so-called sesmix initiative where I'm also collaborating. It's essentially the idea to have a Julia-based stack as part of a bigger effort, a bigger multi-physics effort going all the way from DFT to combustible, to basically combustible flow simulations. And as part of this in particular, there are some efforts to develop further interface packages, for example, to really, in an abstract sense, capture the notion of an interatomic potential. There's, for example, a wrapper around lamps where the hope is at some point to really be able to just slide in these interatomic potentials from Julia. I mean, that's really a bit more of a medium-term effort, I should say, because it's not so simple, but you can at least already interact with lamps from Julia. I mean, that's a starting point. There's some packages for training interatomic potentials that have come up. I should mention, for fairness, that there's really also some other efforts to come up with ways to represent structures. We are in touch with these type of developers. In general, we really try to get at least compatibility with Atom Space as much as possible. There's a bunch of simulation tools, not only in DFT, but also in the relation of, for example, here, quantum dynamics, classical MD, ring polymer methods. Then there's also some quantum chemistry packages which are starting to be developed. ACE Suite I already mentioned. There's also some other ecosystem, the Chemilia ecosystem, where people are working more towards like crystal graph neural network based approaches. And I already mentioned that there's a bunch of let's say parsing packages. So, for example, the LAMPS one, but then there's also packages for workflow management. So there's one bigger effort along this minerals cloud organization. I don't know the people, but I mean, they have a lot of work, which looks quite interesting. At least there's some people from people around here who have done some smaller efforts for parsing DFT codes in Julia. And I should mention that there's also starting to come up a bigger set of support packages, right? So people who are working on new ways to do the very fundamental things like Brilliant Zone integration. People who have come up with tools for really visualizing things like phonons, for example, in k-space paths and so on, like an alternative to the CK-path Python package that you might know. And people like also people here, Austin, for example, is working on a pseudo-potential parser, some pseudo-libraries we have started to collect. I mean, this is essentially just a way, in a structured way, to make pseudo-potentials available from Julia, and so on and so forth, right? So there is really starting to come up various packages in a number of efforts, which, in my opinion, make it now feasible to really start using Julia also for simulations, and not just for playing around. Okay. I think this is all I had to say. We are almost at the hour. If there's more questions, of course, I'm very happy to answer them. Otherwise, I thank you very much for your attention and for coming. And in general, I should really say, in my group, I have a bunch of job openings. So if you're interested to work on Julia, if you're interested to work on mathematical methods for atomistic modeling, particular density function theory, you're very happy to contact me. You're very welcome to contact me, of course, and I'm very happy to speak to you. We have something on numerical methods, and we have something on more Bayesian approaches to understand uncertainties in DFT. So if you're interested, have a look at our website, matmat.org. And thank you very much for your attention. Questions? No questions? Yes, there is one. Please use the mic. Yes.
Hi, thanks very much for the talk. So I have a maybe very general question. So what do you think makes Julia packages so easily to work together? Is it multi-dispatch or
yes.
what's the
Stop. That's
point?
it.
Yeah.
Multiple dispatch is exactly the keyword. So just for people who are not aware of the concept, so multiple dispatch is the idea that essentially when you are selecting what type of implementation to use for a function, which essentially associates a name to whatever you want to do, Julia inspects the type of all the arguments that you're given, right? So this doesn't sound so groundbreaking, if you wish, but in fact it is, because it allows you basically to annotate to each object that you're passing to a Julia function properties, right? So properties like it is a symmetric matrix. You know, that's what we saw with the eigen decomposition. These sort of properties, or, you know, this is a Brillouin zone, like a k-point quantity. You know, that's something we use in DFTK, for example. These sort of properties you can annotate to an entity, and this allows the Julia compiler to select really the best matching method for these type of for the type of operation you want to do, right? So this means that the person who develops the data structure, meaning the person that, you know, says a type has these properties, it knows well how to do this type of operation. These people don't need to talk to the people that really actually do the implementation, right? So you can separate the what from the how, right? You can separate what you want to do, right? The function, compute me the eigen decomposition, right? That's the what. You can separate this from the how. This is like, I know this is a symmetric matrix, so I can use this algorithm, right? This is what you separate. And essentially the people who, like us scientists, who develop an idea, a physical method, they write the what. And then computer scientists and mathematicians, they can figure out the how, right? So we can actually use our strengths very easily, combine our strengths very easily in one package, in one project, but without sort of the mathematician standing in the way of the application person, like, oh, I want to try a new method. So, you know, do you support this? Right? Because Julia brings actually fallback implementations for pretty much everything, right? So if a fast algorithm is not available, at least you will get an answer. You can see your physical model works. You can make it fast later. I always say, first get it to work, then get it to work fast, okay? And this is also like links towards this iterative performance optimization that I've been talking about. In Julia, it's very easy to just come up with a prototypical implementation. You see that your idea, that your method works, and then you figure out where are the slow bits? Where does it sort of stop me from getting to a bigger problem, to getting to my answer quicker? And then you think, or you can go to a mathematician and then think, you can really think like, how can I improve the algorithm in this particular situation? And then you do find one method specifically for exactly the type of properties that you have. And this will sort of seamlessly slide into the implementation that you already have. That's exactly what makes these multiple dispatch so powerful. This allows how you can reuse code from other packages. And this allows this iterative performance optimization that I think is very crucial. Further questions? Yeah, please, in the front.
So, are there some constraints when you do, for example, automatic differentiation, the fact of how you have to write the code?
Yeah, sure. I mean, life is not for free. But there are, I mean, okay. So first of all, there are multiple kinds of automatic differentiation. There's the so-called forward mode. That was the one I was showing and also briefly explaining when there was the question about the type. But there's also the reverse mode or backpropagation that you might have heard of. So backpropagation is a bit more tricky. I don't have the time to go into the details, but there it depends a lot more on how you write your code. So for the forward mode, roughly speaking, if you're willing to live with performance penalties, it sort of always works, right? I mean, I'm saying sort of because, you know, there might be some functions where Julia just doesn't have a proper implementation at the moment. So you might need to write a workaround, you know. I mean, in fact, when we did this forward mode implementation in DFTK, we spend a bit of time to, you know, write workarounds here and there, right? So you have, and we spend some time to adapt the code. But the point is that you don't need to start from scratch, right? So, you know, some of these Python-based solutions out there, they start from scratch to write their code. We didn't have to do that. So our code was there before we started to think about algorithmic differentiation, right? So you need to make some changes, you need to make some adaptations, but it's very little. And in particular, it doesn't require you to split off the code. So it's still one code base, right? So even though we have algorithmic differentiation, we have GPU support, it's still one code base, right? So, I mean, we have a few cases where we sort of dispatch to specific code paths for special cases, but this is really like a almost negligible fraction of the code. So the major paths of the code are really run in whatever mode you use it. It's exactly the same code. I hope that answers your question. Yeah, good. There was another one just over there. Yeah.
Just an inflammatory question. So what do you make of Mojo as sort of an alternative for basically getting Python faster?
Mojo, I think I've heard about it, but I don't actually know what it is.
Okay. Well, my question
well, then explain it. Then I can give you
well, I mean, basically they're claiming to have Python running 10,000 times faster.
Okay. But I would imagine this works by basically re-implementing Python, right? You have to use special Mojo functions, special Mojo types, special Mojo libraries, right?
Yeah, so it's Python plus basically, yes.
Yeah, but okay. Anyway, I mean, I can't comment beyond that.
No,
so
okay.
Yeah, I mean, I know, for example, Number has tried to do things like this. And the issue there was at some point they had, I mean, it's exactly this two language problem. So at some point they had to cut, they had to make a choice. Where do they go back to the Python world, essentially? And I mean, JAX is also doing something like this, right? So in the end, they're passing a tape and then they're working on this tape. But again, this requires you to really like run all the code paths, which means that you need to use special constructs. So the issue is really like Python as a language has dynamicism, but if you want to do custom stuff on top, you have to sort of trick the Python compiler. You have to take the Python compiler or the Python interpreter out of the loop, essentially, right? In Julia, you don't have to do this. In fact, it's quite the opposite. You're using the features of the compiler to do exactly what you want to do, right? So, I mean, I can't really comment on the details because I've never looked at it, but I would say there must be some restrictions. Yeah. All right. Yeah. One more question. The last one, I would say.
If no one else. So I have a question about, can I do for now, like import Python models, like machine learning model or some other models, and still utilize Julia autodiff mechanism?
No,
things like that.
No.
Okay.
That's exactly one of the reasons why, I mean, you know, you can use C libraries and Python libraries from Julia, right? But there's still a reason why we rewrote our code instead of using, you know, I mean, there's other people who have written C-based, for example, the DFT codes, right? So why did we not use their code? And the answer is exactly that. So there's a certain number of features which you can only use within the Julia world. That doesn't mean that you cannot integrate with efforts on the C side. So for example, I showed you this GPU-based DFT computation. So I'm actually using a libc library for exchange correlation functions compiled for GPU in the backend, right? So I have a C version of this exchange correlation library. I have a GPU version, and in the back, my code automatically selects which of the libraries to use depending on whether you're doing the computation on the GPU and the CPU. So if you have a GPU-enabled code, AD-enabled code in another language, well, not in theory, but actually in practice, you can combine that with these efforts in Julia. It is doable, but it's not seamless. So you have to put some effort in. Yeah. All right. I think that brings us to the hour. I thank you very much for your attention. For the people online, I thank you very much for attending. And yeah, I hope to see you soon.